Lecture 3 covers sections 2.1 through 2.3. At the end of today's lecture, you should be able to identify a pure substance. You should also be able to identify phase boundaries for the solid, liquid, and vapor phases on a phase diagram. You should be able to understand a PVT surface that represents our PT, TV, and PV diagrams. And you should be able to identify if a substance is a subcooled, compressed, or saturated liquid, or a saturated or superheated vapor, in terms of your saturation pressure and temperature. For us to begin, we're going to talk about a pure substance. A pure substance is homogeneous and has invariable chemical composition. A pure substance can exist in various phases independently or simultaneously. That is, we can have water existing solely as a solid, i.e. ice, as a liquid, i.e. liquid water, or as a vapor, i.e. steam. Or we could have water existing as a solid and liquid simultaneously, i.e. ice water, or as liquid and vapor simultaneously, i.e. the contents of a pressure cooker. But the chemical composition must be the same in all these phases. That is, we have to have water, and we can't have water with, say, peroxide. However, we are going to consider air as a pure substance as long as there is no phase change processes occurring. Air is primarily nitrogen, followed by oxygen, then some argon, a little bit of CO2, and then some methane, and a whole bunch of other gases. Now, let us begin by talking about our vapor-liquid phase equilibrium. Let's consider the following piston cylinder system shown to the right. We have water contained within our piston cylinder system as designated by the blue liquid. We have a weightless piston that's represented by the shaded gray area that's constraining the water within the piston cylinder device. Our system is initially at state 1 with a temperature of 25 degrees centigrade and a pressure of 101.325 kPa. This is known as standard temperature and standard pressure. Water in this state is existing as a liquid. Now, if we turn on the Bunsen burner beneath our piston cylinder device and we add heat to our system, we will note that our temperature is going to increase, while our pressure is remaining constant. Since we have a massless piston cylinder device, it is able to float freely. Now, as our temperature increases, we are going to have a marginal increase in our specific volume. The density of water does not change too drastically with respect to temperature. This is shown as state 2. As we add more heat, we'll have an increase of our temperature and our specific volume until our temperature reaches 100 degrees centigrade, our boiling point. The pressure still remains constant throughout the entirety of this process, and this is shown as state 3. The system is still completely in a liquid state. We do not have the presence of any vapor. Now, once the temperature reaches 100 degrees centigrade, and we're going to call this our saturation temperature, at a pressure of 101.325 kPa, which we're going to call our saturation pressure, additional heat is needed to change the phase of our liquid water into our vapor. And that amount of heat is known as the latent heat of vaporization. During the process of phase change, both our temperature and pressure are going to remain constant, but our specific volume is going to increase drastically as our liquid water turns into vapor. Recall a vapor state is roughly 1,000 times less dense than a liquid state, so any transformation of our liquid water into vapor is going to drastically increase the volume of our system, and this is shown as state 4. Once all the liquid is transformed into our vapor state, additional heat is required to increase the temperature and specific volume of our system, and this is represented as state 5. Now, once we add more heat, our vapor is going to become superheated, and our temperature is going to increase while our pressure remains constant within the setup. Now, this experiment illustrates a very important relationship between our pressure, temperature, and specific volume. The relationship between our saturation temperature and our saturation pressure is depicted by a vapor pressure curve, which is our pressure versus our temperature, or vice versa. And it's the interface between our solid and liquid vapor regions on our phase diagram. That is, as we went from a liquid state to a vapor state, underneath a constant pressure process, we saw that phase transformation occurred at a constant temperature. This PT diagram does not give us enough information, though, to quantify how much liquid or vapor we have, solely based upon the temperature or pressure within our system. Now, before we begin to quantify our state while it resides on a phase boundary, we first have to identify our 3 phase boundaries within our PT diagram. The first is the fusion line, which is a vertical solid line between our solid and liquid phases. We notice our fusion line starts at our solid liquid vapor interface at our triple point, increases near vertically, and then hooks to the left before continuing to the right. The fusion line is separating our solid and liquid regions. The line that separates our water and vapor phases is our vaporization line. This starts at the triple point and moves towards the critical point. Lastly, the line separating our solid and vapor phases is known as the sublimation line. This line starts at a triple point and moves down and to the left. Crossing these lines indicates that we've undergone a phase transformation. And we can have two different phase transformations per the crossing of a line. And that's dependent upon the direction. If we look at our fusion line, we can have the process of melting, where we move from a solid to a liquid phase. Or we could have the process of freezing, when we move from a liquid to a solid phase. When we cross the vaporization line, we can have two separate processes. Boiling is where we go from a liquid to vapor phase, and condensation is when we go from a vapor to liquid phase. And lastly, when we cross the sublimation line, we can have two separate processes. Sublimation is the process of going from a solid to vapor, or deposition, going from a vapor to a solid. Now let's look at an example of how to use our PT diagram for water. What phase changes can water undergo if our pressure is held constant at a pressure of 50 kPa and 0.3 kPa? Now notice on our y-axis our pressure is represented in MPa. 10 to the 0 would be 1 megapascal. So our pressure of 50 kPa would be below this line. And at 50 kPa, if we draw a line horizontally from our y-axis across, we see that we can go from a solid to liquid region, and we can also go from a liquid to vapor region. So we can have melting and freezing depending upon how we cross our fusion line, and we can have vaporization or condensation, i.e. boiling and condensation, as we cross our vaporization line. Now 0.3 kPa would be 3 times 10 to the minus 4th megapascal, and we see this crosses our sublimation line. So the only two processes that can occur underneath this constant pressure process would be sublimation or deposition, depending upon the direction.